So another interesting applications of the theory of complex numbers in plane geometry is the 9-point circle of any triangle. So before introducing the main problem, I'll give you a theorem, in fact the concept of the Euler's line of any triangle. So what's the Euler's line? In fact, if we consider any triangle ABC and its circumscribed circle, so triangle, the arbitrary triangle ABC, the center of the circumscribed triangle is the point of concurrency of the perpendicular bisectors of each sides of the triangle. So this point consider as O. Another point is the orthocenter of the triangle, which is the point of concurrency of the altitudes of the triangle ABC. So this is H, the orthocenter of the triangle ABC. I'll name this D, E, F, and I, J, and K. And another point, another interesting point in any triangle is the centroid. So the centroid is the point of concurrency of the medians. The median is the line connecting each vertices to the middle of the opposite side. So if I connect B to E, because E, D, and F are the midpoints of each side, so BE, CF, and AD are concurrent at a point G called centroid or center of mass of the triangle ABC. So the theorem is that these 3 points O, G, and H are collinear, and the line connecting these 3 points is called Euler's line. So in order to solve this problem, before introducing the main problem of this lecture, I consider without loss of generality that O is the origin of the complex plane that we consider. So O is 0, 0. I consider the equation of the line passing through the points A and D, for example D1, and the equation of the line D2 connecting B and E, and the line BCF D3. So if I consider, for example, D1 passing through ZA and Z of D, we know that D is the midpoint of the line segment BC. So Z of D is simply Z of B plus Z of C over 2. So the equation of line passing through these 2 points is Z minus Z of D is equal to Z of A minus Z of D over Z of A bar minus ZD bar times Z minus ZD. Similarly, I consider the equation of D2 passing through ZB and ZE, this point, which is equal to Z of A plus Z of C over 2. The equation of this line is Z minus ZE equal to ZB minus ZE. Sorry, over ZB bar minus ZE bar times Z minus ZE. And finally Z3 passing through ZC and ZF, the midpoint of the line segment AB. So Z of F is ZA plus ZB half. So the equation of the line D3 is Z minus ZF equal to ZC minus ZF over ZC bar minus ZF bar times Z minus ZF. We can show that the point which satisfies simultaneously this system of equation is the point Z, which is Z of the point G, in fact, the intersection of these lines, D1, D2, and D3. So Z of G, which is equal to Z of A plus Z of B plus Z of 3 over 3. So we have obtained the formula which give us the coordinates of the centroid of the triangle ABC in terms of the coordinates of the vertices of the triangle. So this is simple because if we consider the intersection of these two lines, this will be this point, and this point will satisfy this equation. So we have calculated the point, the center of mass of each triangle. It's the component corresponding to the center of mass of the triangle in terms of the component of each of the vertices. So the second problem is to identify the orthocenter of this triangle, the point H. So to do this without loss of generality, I consider that the circumscribed circle of the triangle ABC is a unit circle. So the radius of this circle is equal to 1. And I know because A, B, and C belong to the circle, to the unit circle C. So norm the modulus of Z of A is equal to modulus of Z of B, Z of C, Z of A bar, Z of B bar equal to Z of C bar. These are the distance between the points A, B, C and the origin. And these will be 1. These in fact are the radius of the circumscribed circle, which is 1. We consider the line passing through AI and the line BC. As we know, the equation of the line which passes through the points A and B and C, due to the fact that B and C belong to the unit circle C, we can describe the equation of the line BC as Z minus ZB, ZC, Z bar equal to ZB plus ZC. And the equation of the line AI, in fact A is the point C that we have introduced in our formulation, and the line AI is perpendicular to line BC. So the equation of the line AI will be as Z minus ZB, ZC, Z bar is equal to ZA minus ZB, ZC, ZA bar. So the intersection of these two lines is the coordinates or the component corresponding to the point I. simply we can solve this system of equation, and z, which is simply z of I, the intersection, is z of a plus zb plus zc minus za bar zb zc half. And with the exact approach, with the exact same approach, I'll have z of j and z of k, which are the intersection of the lines AC and BJ and AB and CK, sorry, which will be equal to ZB plus ZA plus ZB plus ZC minus ZB bar ZA ZC half and ZA plus ZB plus ZC minus ZC bar ZA ZB half. So now I can consider the equation of the lines AI and CK, for example. AI and CK. And finally BJ. The intersection of the lines AI and CK is the point H, which will be situated in the line BJ, and we can verify this. So the equation of the line AI is Z minus ZI equal to ZA minus ZI, ZA bar minus ZI bar times Z minus ZI. The equation of the line CK is Z minus ZK equal to ZC minus ZK over ZC bar minus ZK bar times Z minus ZK. Sorry. In which we know the ZI, ZK with these formulas. So the intersection of these two lines is Z is equal to Z of H, which can be obtained simply as Z of A plus Z of B plus Z of C. So we have calculated the orthocenter, the component corresponding to the orthocenter of the triangle ABC as a function of the components of the vertices of the triangle ABC. So we can simply show the theorem, the Euler's theorem, which states that if O is the center of the circumscribed circle of the triangle ABC, G, which is the centroid of the triangle, and H, which is the orthocenter of the triangle ABC, the first interesting thing is that the distance OH is 3 times the distance OG. And this is simple. This is straightforward because OH, the component corresponding to O is 0, 0. The component of G is ZA plus ZB plus ZC over 3. And this is ZA plus ZB plus ZC. So the length of the line segment OH is equal to ZA plus ZB plus ZC, and the length of the line segment OG is ZA plus ZB plus ZC over 3. So we have this interesting equation. And the second result is that if we consider the vector OG and the vector OH, OG will be simply ZA plus ZB plus ZC over 3. This is the complex, this is the representation of the vector OG in the complex plane. And OH, which is ZA plus, which corresponds to ZA plus ZB plus ZC. So we observe that OH is 3 times OG. So the vector OH is a real multiple of the vector OG. So the real multiplication corresponds to dilatation or contraction. Here is the dilatation. So the points O, G, and H are collinear. And the line which connects these 3 points, the name of the line is the Euler's line of the triangle ABC.